The Hyperspectral Radiography Sources program is seeking to develop a suite of laser-driven radiation sources. By using a common laser to drive these multiple sources, one can gather more information about the structure being scanned. X-rays, protons, electrons, ultraviolet, and positron radiation probe for different material defects. DoD systems are increasingly relying on non-destructive evaluation techniques to increase the serviceable life of military platforms. The Hyperspectral Radiography Sources program is seeking to develop a suite of laser-driven radiation sources. The common piece of all of these sources is an ultra-intense femtosecond laser pulse. To amplify the short pulse, one must first stretch the pulse in time by making some of the wavelengths of the pulse travel longer than others in a device called, appropriately enough, a pulse stretcher. The pulse then travels through an amplifier to boost its energy and is then sent through a pulse compressor that reverses the process of the pulse stretcher. The compressed pulse can contain over a joule of energy while still being less than 100 femtoseconds long. The resulting intensity approximates environments not seen outside the core of stars. These ultra-intense, ultra-short pulses will be used to seed radiation modules in the HRS program. The Hyperspectral Radiography Sources program is developing high-brightness monochromatic electron beams using a technique called laser wake-field acceleration. In this process, a very intense ultra-short laser pulse is fired at a helium gas jet. The laser pulse creates a plasma in which the electrons of the gas are separated from the atoms. The oscillating electric field of the laser pulse causes the particles in the plasma to form a wake, like a boat moving through the water. The electrons, having been separated from the atoms, ride on this wave much like surfers catch a wave into the beach. These electrons are accelerated to nearly the speed of light, with beam energies as high as 1 GeV having been demonstrated. The HRS program will turn these proof-of-principle experiments into usable electron beam technology. The Hyperspectral Radiography Sources program is developing high-brightness monochromatic X-ray beams. A portion of an intense ultra-short laser pulse is focused on a gas jet to produce a bright electron beam. Another laser pulse is focused onto the bunch of electrons. The photons of the laser pulse scatter off the electrons, producing monochromatic X-ray pulses. These monochromatic X-rays will be useful probes for medicine and material evaluation. The Hyperspectral Radiography Sources program is developing extreme ultraviolet light sources. A femtosecond laser pulse is sent into an optical cavity whose length is matched precisely to the round-trip time of the pulse. If the phase and timing of the next laser pulse matches the pulse that traveled around the cavity, the intensity of the two will add. Eventually, the light in the cavity becomes sufficiently intense to enable high harmonic generation, in which the electrons in the atoms of an inert gas jet scatter off the atomic core, producing intense pulses of ultraviolet light.